Hello again. This is video lecture 15.3, and we're going to focus on chapter 15, section 5, in which we're going to have oscillating systems that are called pendulums. The singular is pendulum. In this day and age, most people use the plural pendulums, but you'll also come across the more old-fashioned plural pendula. Okay, so it turns out it's convenient to take any pendulum and categorize it into one of two groups. The so-called simple pendulum, which is the simplest to analyze and the one we'll talk about first, and the more common physical pendulum. But let's talk first about the simple pendulum. Okay? Simple pendulum. What do we mean in physics when we say we have a simple pendulum? It means we're going to have an object oscillating in a gravitational field directed vertically down, and it's going to consist of a massless string or cord of some length L and a smallish object of mass m at the end of that cord. And we're assuming all the mass of the pendulum is in that object at the end. And in some cases, you'll see that object at the end of a simple pendulum called the bob, B-O-B. Okay, and so let me show you a Wiley Plus animation of the oscillation of a simple pendulum, so just so we're clear what it is we're talking about. So here we have a schematic representation of a piece of string that has been tied at one end to a, say, like a ceiling of some kind, and the bob is represented by the red disc at the end. That's where the mass m is, and the string has some length L. And in fact, by default in this animation, the length L is 2 meters, and the mass m of the bob is 1 kilogram. And vertically upward is shown. Vertically downward, of course, is the opposite of that. The dashed vertical line is vertical, so for reference. And apparently what we've done here is we've taken the simple pendulum and pulled the bob out some angle theta from the vertical, as you see right there. And when I run the animation, we're just going to let go. And you can think a minute about the forces acting on the bob. I contend there are two forces acting on the bob. Can you name them? One of them is the force due to gravity, and that force is going to cause the bob on that fixed length string to oscillate about that pivot point. Okay, so let's run the animation here so that we can see what I'm talking about. There, we've released the bob, and now it's just oscillating about the vertical. Okay, now the graph below shows the angle of that string measured from the vertical in degrees as a function of time. And it turns out that we started that at 30 degrees. It's a little bit on the large side for an angle in a simple pendulum, as you'll see in a minute, but it's still not too bad. And the main thing I want you to notice about that shape of that plot of angle in degrees versus time is that it looks what a physicist would call sinusoidal. In fact, it looks like a cosine curve. Does it not? In fact, it is. Okay? That's a sign that we have simple harmonic motion. We've got a variable here. It's an angle. It's a theta, not an x. But it's varying sinusoidally. So that's a strong hint that we have simple harmonic motion going on. Okay? All right, now. Okay, now what I'm going to do is I'm going to reset the animation, and I'm going to click this box, Show Forces on the Bob. In other words, it's going to draw a free body diagram for the bob. So I asked you a moment ago, can you identify the two forces that are acting on the bob? We said one's F grav. What's the other one? Did you say the tension in the string? Let's show the forces. So the one pointing straight down, we can get it to highlight. You can just barely see it there, F grav. And the one on the bob pointing upward along the string towards the support is the tension, T arrow. Let's see how the forces change, if at all, when I run the animation. Watch the forces now, the force arrows. That's pretty interesting. Of course, F-grav doesn't change as the bob oscillates. It points vertically downward, and it has a magnitude equal to m times g, where the m is 1 kilogram, and the g is 9.8 newtons per kilogram. So m times g is 9.8 newtons, vertically down. But the tension force, did you notice that arrow? Watch it closely. Now it's always pointed along the string towards the support, but its magnitude changes during the course of the swing. So the tension force is somewhat complicated to deal with, isn't it? All right, but what we want to understand is why this is oscillating and how we can describe the oscillations quantitatively. So now I want to go back to my picture, and you'll see down there in the lower left corner, we've got a free body diagram for the bob part of the simple pendulum. And we're going to apply Newton's second law to that bob. But because the tension forces would be pretty tricky to work with, I don't want to use Newton's second law for translational linear motion, even though it's valid. It's going to be a bit complicated. Let's use Newton's second law for rotational motion, which is right here. Let me remind you. Angular acceleration equals net torque over rotational inertia, where the net torque and the rotational inertia must be calculated about the same axis or point. Let's use that. And let's calculate the torques and the rotational inertia about the pivot point of the pendulum, up there at the top. I'll emphasize it there with the big black dot. All right, so now let's look back at the forces acting on the bob, and let's think about torques about the pivot point from each force. Now we see why I wanted to use the rotational version of Newton's second law. Look at the tension force. Look at its line of action. Look at its line of action. I'll draw it a green dashed line. The line of action of the tension force passes right through the pivot point, which means the tension force has no moment arm, which means the tension force produces no torque about the pivot point. And therefore, the fact that the tension force is a somewhat complicated force to deal with doesn't come into play if you use the rotational version of Newton's second law. In fact, the force that's producing the torque about the pivot point is F-grav, which is vertically down. Okay? So that's the only force producing a torque. Let's write down an expression for that torque. Here's the line of action for F-grav, going straight up. Then the moment arm, remember, is the perpendicular distance from the axis of rotation to the moment arm. There, right there, is the moment arm for F-grav. So the magnitude of this torque, the magnitude of the gravitational torque, tau grav, is moment arm times magnitude of gravitational force. Now we know the formula for the magnitude of gravitational force. It's our old friend mg. What is the moment arm? Well, that's why I drew it in that picture, because we got to be able to write that down. How long is that red line that I've marked as the moment arm? Note what we know is the length L of the string. Assume that's known. And the angle theta that the string makes with the vertical, which, by the way, if you see the theta in the drawing, is also that angle right there. That's also theta. So then, look at this right triangle right here with these sides. Right there. The moment arm is equal to hypotenuse times sine theta. L sine theta. There's your moment arm. Now that's the magnitude of the torque. I got to get the direction, which we'll account for by a sine. This force wants to cause clockwise rotation, so we put a minus sign with it. And so then we get this expression right here for the angular acceleration of the pendulum. Minus mg L sine theta, all divided by I, the rotational inertia. Now that is a formula for the angular acceleration, and it depends on the angle theta, but in a somewhat complicated way. It depends on the sine of theta. That's a bit messy. We're not ready to deal with something like that. So we're going to add one more restriction in our analysis of a pendulum. We're going to restrict ourselves to small values for the angle theta. Okay? For small theta. Now the theta is going to be measured in, I'm going to talk about it as being measured in radians. So when I say I want to have small theta in radians, what I mean is that the angle theta is quite a bit less than 1 radian. It's small compared to 1 radian. I'll remind you how big 1 radian is in degrees. It's approximately 57.3 degrees. Well, 57.3 degrees is a pretty big angle. So if you measure it in degrees to say you need a small angle, 10, 15, maybe 20 degrees, not a problem. Okay? Now, so what if we limit ourselves to small angles, small values of theta, theta small compared to 1 radian? What does that do for us? It does something quite important, and you'll learn the mathematical reason behind it. If you've had enough math, you will have learned about something called a power series or a Taylor series. And what you learn when you study power series / Taylor series is that the power series for sine theta enables you to approximate sine theta when theta is small in radians with just theta itself. Sine theta is approximately equal to theta when theta is much less than 1 radian. Now that takes a little getting used to. So the first thing I suggest you do is just check it. Get a calculator, put your calculator in radian mode, and take the sine of an angle that's small compared to 1. Let's take the sine of 0.1. That's small compared to 1. So I take the sine of 0.1 and I get 0.0998. In other words, approximately 0.1. So sine theta is approximately equal to theta. Your calculator can help you at least just simply verify that, if the theta is small. If we make that approximation, it's called the small angle approximation, then the rotational version of Newton's second law becomes substantially easier and more easy to interpret. It says that the angular acceleration of the simple pendulum is given by negative. I've grouped together all the things we'll consider to be constants. Mass m of the bob, g, the length L of the string, and the rotational inertia of the pendulum, all grouped together, considered to be constants, times theta. This is what your textbook calls the hallmark equation for simple harmonic motion, because it has the form, at least in the rotational case, angular acceleration equals a negative constant, which is in fact the angular frequency squared, times the angular displacement from equilibrium. We need to be able to recognize that equation when it appears before us. And it has just appeared before us in the line right above. Alpha equals negative, stuff grouped, mgl over I times theta. That is exactly this hallmark equation. And the minute we see that hallmark equation, we know we have simple harmonic motion for the variable, in this case, theta, the angular displacement. We can conclude that immediately. No more mathematical manipulation is required. The minute we observe the hallmark simple harmonic motion equation, then we know that theta, that variable, oscillates sinusoidally. We can in fact write down that expression right there. Theta as a function of time will have the form theta max, maximum angular displacement from equilibrium, if you like the angular amplitude, times cosine of omega t plus phi, where omega is the angular frequency. And, note, the angular frequency squared is what's sitting between the negative sign and the theta, which in our equation, look right up above, is right there, mgl over I. That's the angular frequency squared. So that I can immediately say the angular frequency of these oscillations, omega, is the square root of mgl over I. You see how we got that? All from the hallmark equation for simple harmonic motion. All right, so here's something that does not look at all like a block connected to a spring. Yet it has a variable, in this case it's an angle, that oscillates with simple harmonic motion. And we know what determines the angular frequency of that simple harmonic motion. Sure looks like M, G, L, and I. However, for a simple pendulum, it's actually even simpler than that. Let me take another step in the omega formula. The simple pendulum has a point particle. The bob is a point particle, a point mass. Mass m, that's a distance L from the axis. Well, we already know how to calculate rotational inertia for a point particle. That's a known distance from the axis. Take the mass times that distance squared. So in the next step here, I'm going to replace the I, rotational inertia, for a point particle with ml squared. Then a pretty amazing thing happens. The factors of m cancel, and one factor of L cancels. And I get a very simple formula for the angular frequency of the simple pendulum. Square root of G over L. The m is gone. The angular frequency doesn't depend on the mass of the bob. It depends on only two things. What's the value of little g, where your pendulum is, and how long is the string? Now, once we have a formula for the angular frequency of an object, we also have a formula, or can get a formula, for its period, the time for one oscillation, capital T. Because remember this simple result. Period is equal to 2 pi over angular frequency, omega. And then plug in our formula for omega, and we get a very well-known formula, the period of a simple pendulum. 2 pi square root of L over G. So the period of a simple pendulum does not depend on the mass of the bob, but it does depend on the length of the string, and the longer the length, the longer the period. This, if you've ever graded elementary or middle school science fair projects, is one of the quintessential experiments that the children do. If you go to a middle school, if you would someday judge a middle school or elementary school science fair, it's almost inevitable that at least one of the experiments will be something like, what determines the period of a pendulum? And they were probably looking at a simple pendulum. Let me go back now to the animation, and let's look at that oscillation again, and let's look at the period. So there we are. I've run it already. You can see the cosine shape of the theta oscillations, right? And because we released the pendulum from rest at its maximum angle, this happens to be 30 degrees, that phase angle, phi, in the argument of the cosine is 0. And so the equation that describes that theta graph is just theta max times cosine of omega t, where omega is equal to 2 pi over the period. Let's look at the period here, okay? Let's just try to estimate it. How long, how much time to repeat? Well, we start at time 0 at 30 degrees. How much time to get back to a theta of 30 degrees? Looks like it's just a little less than 3 seconds. You see what I'm saying? All right, I'm going to reset the animation, and I'm going to change the mass. Let's make it as big as we can. 3 kilogram mass. Notice the force vector arrows changed. But now let's run it and see if the period has changed. It hasn't, right? It's still just a little under 3 seconds. The period was not affected by the mass. All right, now let's change the length of the string. Let's make it longer. It's currently 2 meters. Okay, I've made it 3 meters. Now let's run the animation. The period is clearly longer. It's now roughly 3.5 seconds. What if I make the length of the string as short as I can, 0.5 meters? Now it's got a very short length. What should the period be like? Very short now, isn't it? Okay, so the period does depend on the length of the string, but not on the mass of the bob. Let's do just a little more practice with a simple pendulum. Because let's remember another idea that we can bring to bear to study a simple pendulum that I haven't yet said. As the bob swings, we know there are two forces acting: gravitational force and tension force from the string. Tell me which of those does work on the bob as it swings. What you think about that? Did you say that it's only F-grav that does work? We've actually talked a little bit already about pendulums in Chapter 8. And we applied, Chapter 7 and 8, and we applied work and energy ideas to a pendulum before. And we explained back then that the tension force on a swinging pendulum like this actually does zero work. Because the tension is along the string, and if you just imagine a little infinitesimal displacement of the bob, it's always tangent to the circular arc, which is perpendicular to the string. And so that displacement is perpendicular to the tension force. And when a force is perpendicular to the displacement, you get no work. So again, that complicated tension force that I could see in the animation doesn't do any work, so I don't have to worry about it if I use energy ideas. The only force doing work is F-grav. And so if I take the system to be the bob plus Earth, the mechanical energy is conserved for a pendulum. So we can bring back another key idea. E mechanical picture 1 will equal E mechanical picture 2 for whatever 2 points I want to study, 2 pictures. So that's where this practice is headed. Here's what it says. We have a simple pendulum swinging back and forth as the drawing is implying, and at a certain moment when the angle theta of course is right here, the angle of the string measured from that vertical reference line, when the angle theta is positive 1 degree, positive angle means it's been measured counterclockwise from the vertical. When the angle theta is positive 1 degrees from the vertical and descending, that means the bob is actually moving that way towards the bottom point. It has a kinetic energy of 3 joules and a gravitational potential energy of 2 joules. With a reference level for potential energy set as 0 at the lowest point in the bob's path. So if I estimate the lowest point in the path to be roughly down there, that's where the bob would be when the string is vertical. That line corresponds to U grav equals 0. So if I take that picture to roughly represent what this is talking about, theta is 1 degree, then I know that at this moment, if we call this picture 1, the kinetic energy is 3 joules, and the gravitational potential energy is 2 joules. That's my picture 1. Note then the E mechanical in picture 1, K plus U, is 5 joules. That means that the value of E mechanical at any other time I choose to look at, any other picture I choose to draw, the E mechanical has to equal 5 joules. Well, let's look at some of these questions then. Question A. What is the kinetic energy when the pendulum is at theta equals 0? Well, let me come over here to the side to do A, and draw picture 2. That represents the bob just as it swings through the vertical, like that. And of course, it'll have a velocity to our left during this swing. That's my picture 2 then, okay? And the question is, what's the kinetic energy in that picture? Because the theta is 0 there, yes? Well, I know E mech 1 must equal E mech 2. But E mech 1 is 5 joules. Now what about E mech 2? Well, in general, that's K plus U grav. But if I'm here at picture 2, note the U grav is 0, right? Because it's at that low point. So the energy is entirely kinetic. So the 5 joules is all kinetic. So that's the answer to A, right? What's the kinetic energy when the pendulum's at theta equals 0? All the mechanical energy is kinetic, so 5 joules. That's A. That's it. B. What is the potential energy when the pendulum is at theta equals -1 degree and the bob is rising? Let me draw a new picture. I'll need some space here. Okay, now we're doing B. So I'll draw what I'll call a new picture 2. There's the vertical reference line. Now, a negative angle with the pendulum means it's measured clockwise from the vertical. So that means it's over on this side. And the angle going this way is the angle they're talking about, 1 degree clockwise. And it's rising, so it's swinging up that way. And they're asking me for U grav in that point. Okay? All right, the key thing is that that's still a theta of 1 degree. Now, when I had a theta of 1 degree on the right side, that's the picture over on the right, I'm told the U grav is 2 joules. It doesn't matter then whether the pendulum's on the right side of vertical or the left side of vertical. The bob, if it's a 1 degree, if it's the same angle on either side, 1 degree on the right side of vertical or 1 degree on the left side of vertical, the bob will be at the same height above the low point, and therefore the U grav will be the same on the left side at a 1 degree angle as it was on the right side at a 1 degree angle. So U grav is 2 joules, just like it was when the bob was on the right side at a 1 degree angle. That's answer 2. Okay, or answer B. Question C. What is the potential energy when the pendulum is at plus theta max? Let's draw a new picture. A new picture 2. New picture 2, where we're clearly showing what we're taking to consider for the picture. Plus theta max means the angle's on the right side, like so. Theta max is the maximum angle that it reaches. So that means the bob is up at this angle theta max and momentarily at rest at some height above my reference level. And I want to know the gravitational potential energy. Well, let's use E mech 1 equals E mech 2. I already calculated E mech 1, 5 joules. E mech 2 means K plus U grav. But in my picture 2, we're at the highest angle, which means it's momentarily at rest. So the kinetic energy is 0. So that's all that's left is U grav. In other words, all the mechanical energy is 5 joules. So U grav is potential energy is 5 joules. All right, so the purpose of this practice was just to say, hey, you know, we've learned a lot of physics up to this point, and a lot of these ideas are still useful, and a pendulum system is one for which mechanical energy is conserved. So we can use that approach whenever it is convenient. By the way, I was able to calculate, based on the given information, what the theta max value is in degrees. If you want to try a little challenge for yourself, see if you can figure it out. I'll tell you what I got. The theta max angle is 1.58 degrees. That's what I got. You can try that for fun if you want. Now that's a simple pendulum. It's got a massless string of length L and a bob that's basically a point particle with all the mass at the end. Now I want to talk about what's called a physical pendulum, which is in nature the more common situation. A physical pendulum is just a pendulum where the mass is distributed along its entire length. The mass is not just located down at the bottom. And so the picture that your book shows here is something that looks kind of like a club or a bat or a bowling pin, something like that. And it's been pivoted about an axis of rotation O, which really could be anywhere, but they're showing it up kind of near the top. And then there's really only one other point that is important, and they've labeled it C. And they've marked where it is for this object, but the thing is that it's the location of the center of mass of this pendulum. And why is that important? Because that's where we assume all of F grav acts. There's F grav vertically down. All of F grav acts at point C, the center of mass. And there's the dashed vertical line for reference. And if I displace the pendulum at some angle theta away from the vertical and let go, it will oscillate. And what I want to show is that as long as the angle theta is small in radians, the oscillations are simple harmonic motion. And we do that by applying, just like we did for the simple pendulum, Newton's second law rotational version, and limit ourselves to small angles. In other words, angular acceleration equals net torque divided by rotational inertia, where both the net torque and the rotational inertia are calculated about the pivot point O. And yes, there's a force on that club thing from the pivot point O, whatever that support is. But it produces no torque because it has no moment arm. The only force producing a torque is F grav. And I've drawn the line of action of F grav, and I've drawn the moment arm in red. But I'll draw it again right there. There's the moment arm. So to get the torque, starting with the magnitude, I take the magnitude of F grav, mg, times the length of the moment arm, the length of that red line. How long is that? Well, I do need to know two things. What's the angle theta? And what is the distance from, in a straight line, from the pivot point O out to where the center of mass is? The book calls that distance, it's a little hard to see here, so I'll write it bigger, h. They just use that symbol h to represent the straight line distance from the axis of rotation O out to the center of mass of this physical pendulum. Then the moment arm, the length of the red line there, is h times sine theta, because this angle right here is theta. So our torque magnitude is m times g times h times sine theta. And it's clockwise, so the torque is negative. But then I use small angles for theta and replace sine theta with theta and group all the constants together, and this is the version of Newton's second law for rotation that I get. Alpha, angular acceleration, equals negative, bunch of constants, mgh over I, times theta, the angular displacement. And that again is the hallmark equation of simple harmonic motion. Angular acceleration equals negative constant, that constant is the angular frequency squared, times the angular displacement. It has that form. We need to be able to recognize that. The minute we recognize that our angular acceleration equation from Newton's second law is of the hallmark simple harmonic motion form, boom, we know that that pendulum is going to swing with simple harmonic motion, and that the formula for theta as a function of time can immediately be written down right there. You can just write it down. Theta of t equals theta max, the maximum angular displacement, times cosine of omega t plus phi. And we know what the omega is, because the angular frequency squared, omega squared, right here, is whatever sitting between the negative sign and the theta. In this case, mgh over I. That's omega squared. So the angular frequency omega is the square root of mgh all over I, where the rotational inertia is calculated about the pivot point O. That means we can get a formula for the period of the physical pendulum, using the fact that period capital T is 2 pi over angular frequency. And so here's the formula for the period of a physical pendulum. 2 pi square root of rotational inertia I over mgh. I have a couple of things to say about that. Here's the first one. Note, in this section, whether we're talking about a simple pendulum or a physical pendulum, the restoring force / restoring torque is coming from gravity. I'll show you in the class an example of a physical pendulum where the restoring force doesn't come from gravity. So be careful. This whole section is predicated on the understanding that the restoring force, the restoring torque, that's trying to bring the thing to equilibrium is coming from gravity, F-grav. All right. Now, let's look at the formula for the period of a physical pendulum, because it's pretty famous as well. And at first glance, we would be forgiven if we were to look at that and say, oh, well, apparently, unlike with the simple pendulum, the period of a physical pendulum depends on the mass of the thing, because there's an M downstairs. But it's actually a little more subtle than that, because, actually, remember back at the simple pendulum, we had an M in the formula for omega, and therefore in capital T, but then when we plugged in the expression for I, the rotational inertia, it had an M, and the M's ended up canceling. You see what I'm saying? Well, the same thing happens here, even though it's not immediately obvious. What I'm telling you is that the expression for I, the rotational inertia for this thing, it may be complicated, the I expression, because I don't know exactly what shape that physical pendulum has, but I can tell you this. No matter what shape it has, the final answer for the rotational inertia will be of this form. There might be some constant c, then there'll be the total mass of the thing times some length squared. It's going to have that basic form. There could be a constant, the total mass times some length squared. And when you put that in for I, up here in the period formula, then there'll be an M upstairs and an M downstairs, and the M's will cancel. So the period of the physical pendulum, like that of the simple pendulum, is actually independent of the pendulum's mass, even if it doesn't look like that with that formula. But the period does depend on the shape of the thing and how far the center of mass is from the axis of rotation. Now, one of the things that's kind of handy about a physical pendulum, and we've done lab exams on this and sometimes lab experiments on this, is that you could use a physical pendulum as a device for measuring the value of little g wherever you are. Because the period depends on little g, and if you make a physical pendulum that has a simple shape, like a uniform rod or stick, then you can get a simple formula for I. You can measure the period by just timing it. You did that with the ballistic pendulum. And then you can measure the period, measure the length of the thing, and end up solving for g, i.e. you're measuring g. And if you had a physical pendulum that was really sensitive, you could take this physical pendulum to different locations on Earth's surface and measure the period of oscillation there, and end up then measuring G at that location. And thereby measuring the local value of G where you are. Geologists like this idea because the local value of G tells you information about what the kinds of rocks are that are around there. Now it's actually, that's called a gravimeter. It's actually a lot more complicated than that, but that's a basic idea that you could use a physical phenomenon, in this case, the oscillations of a physical pendulum, as a way to measure the local value of G. All right, so the next practice is meant to see if you've taken to heart the fact I just said about mass and period of a physical pendulum. Here's what it says. We've got 3 physical pendulums. They have different masses, m0, 2 times m0, and 3 times m0. But otherwise, they all have the same shape and size and are suspended at the same point. So just think of this object right up here. Got 3 pendulums. They all have the exact same shape and size and pivot at about point O. But they must be made of different materials because they have different masses. m0, 2 times m0, and 3 times m0. Okay? We are to rank the masses according to the periods of the pendulums, largest to smallest. What would the ranking be? Pause the video, think about it, get an answer, and then come back. Okay? All right, so the formula for the period of a physical pendulum is 2 pi times the square root of the rotational inertia times the mass times G times the distance h from the center of mass to the pivot point. And again, it looks at first glance like there's an m dependence in the denominator, and a bigger mass means a smaller period. But it's not so, because there's also m dependence in the rotational inertia. And the combination I over m, the m dependence cancels out. And the period formula is actually independent of mass. And since we're told that the 3 pendulums have exactly the same shape and size and suspended from the same point, they're all going to have the same period. So the period of pendulum 1 will equal the period of pendulum 2 will equal the period of pendulum 3. All right, now we will be talking about pendulums in our class session, but I'm going to leave you in this video for now with a class engagement question that you will answer on Blackboard. Class engagement on Blackboard. Here's the scenario. It's going to be about physical pendulums, as it says. The picture below shows 3 physical pendulums. They consist of identical uniform spheres of the same mass m that are rigidly connected by identical rods of negligible mass and length d. Right, here's one of the spheres right here, m. Here's another, m. Here's the rigid rod. It has no mass but length d. You may ignore the radius of each sphere in comparison with the distance d. Treat each sphere as a point mass. It has mass m, but it's small in size. Each pendulum is vertical, right? This is the vertical direction, and can pivot about the suspension point O. And you got to look carefully where that suspension point is for the 3 A, B, and C pendulums. Okay? All right, and here come the things I want you to do. A, I want you to write down an expression for the rotational inertia, I, right? For each pendulum about its pivot point O. You've got to look where the pivot point is for each one. The answer will be in terms of M and D. Okay? B, write down an expression for the distance h of each pendulum's center of mass from O. Okay? What is h for each pendulum one by one, where h is the distance from the center of mass of that physical pendulum to the pivot point O. And then lastly, C. Write down an expression for the period capital T of each pendulum's small angle oscillations about O. I will give you a hint. The period expressions that you get will be in terms of D and G when all is done. And then use those expressions to rank the three periods, largest to smallest. How does the period of A compare to the period of pendulum B compare to the period of pendulum C? Those are what I'd like you to enter as your answers on Blackboard for this class engagement. And then we'll talk about pendulums in our next class meeting. That's all for this video.